All right. Hi, folks. Welcome to the Building the R Community 2 session. I apologize that we're starting a little behind. We've got one speaker who I think is here as an attendee but isn't showing up on my speaker list. So I think we're going to swap the order of the talks and we're going to start off with who is scheduled as our second speaker, Neil Batra, who is the president of Applied Epi. And I think I'll just let Neil take it away. And now I cannot hear you, Neil.
Oh,
I think
I was
maybe.
muted.
Hi. Okay.
It's great to be here. Thank you. Let me just share my screen.
Yeah.
All right, you can see the screen?
Yes, looks great.
Okay. Well, it's really a pleasure to be here. So my name is Neil Batra. As you said, I'm the president of Applied Epi, which is a nonprofit organization supporting epidemiologists and really focusing on expanding access to R among public health. So my presentation today, I'm going to focus on the community building and sort of elevation of R we've done within the public health community. And then I will also touch a little bit on the technical aspects of the materials we've created. But since this is about community, I'm going to focus on that. So the general premise to this conversation I would like to have with you is that most epidemiologists around the world are under-equipped for the kinds of outbreak response and sort of applied disease control that they do every day. And they're using substandard tools, typically point and click in most of the world, Excel, SPSS, or they're very expensive with license fees. And overwhelmingly, these practitioners of public health want to use R, but there is a lack of training and support among public health for R use. So we're trying to do that. Now, it's important to start with a quick overview of epidemiology because some people are not aware that there's, I guess speaking very generally, there are two spheres. There's an academic space where there's a lot of really in-depth science about causal modeling and understanding risk factors. And in this space, R is very widely accepted and resources are available for training in R. However, where we work is the more applied or practice side of epidemiology. These are usually people working in local health departments or ministries of health. Operational insight is key. Analysis is often very simple and descriptive. It's very fast-paced. You're often working in emergency contexts. And in this setting, our adoption is really hindered by a lack of relevant training. And so that's the gap that we're trying to address. We're focusing on those frontline public health practitioners by making tools. So really at this point, we're advocating R, training that is, like I said, relevant to those field practitioners that are often coming in with very minimal computer science training, and they're making simple descriptive analysis and applying their epidemiological insights to what they're doing. We want to build support for the local capacity. And again, this is all over the world. And then the other side of our operation besides R is those epi methods, the science behind outbreak response, and making sure that as we bring in R as an open source free thing, we also end up standardizing the methods that are used to do this kind of work. And I think I'm just going to spend a moment and talk about our organization, and then that will set us up for talking about R. We have about 170 team members in 40 countries. Most of us are practitioners and have been for decades in sort of this response side of public health. And so that guides the materials that we're developing. We're not so much in an academic setting as we're in that practice space. We are R experts and also have R learners and beginners because those are really important as we design our training materials. Many of us are data science educators, and as you can see, we're based all over the world. And we have extensive partnerships with local health agencies, but also big organizations like the WHO, Doctors Without Borders, US CDC, and many others. So the need for R training in this space is really clear. We've done a survey of field epidemiologists in low-income countries. Overwhelmingly, they are felt constrained by their use and training in point-and-click tools that I mentioned earlier. Overwhelmingly, they said R training needs to be a high priority, and only 12% said that their agency had sufficient capacity to actually train people in R. And they recognize that it is the gold standard, but there's a clear gap here. In public health in particular, the impact of R is game changing. A lot of what we do is, for example, these situation reports for an outbreak. These are created at a very fast pace, sometimes multiple times a day. There needs to be updates sent to decision makers, whether you're working with cholera or Ebola or COVID. And so R Markdown is a really important tool. One example of this, I was working last September in Haiti on the earthquake response, and I worked alongside a Haitian epidemiologist, and he explained that using the EPI-R handbook that we produced, he sort of self-taught himself R and transformed his 30 hours a week of disease surveillance data management into just 30 minutes, right? And so this was really game-changing for him in terms of freeing him up to do bigger picture work and making his work more reproducible and error-free. And as you all know, R is not just a tool, but it's an open source culture. And I think this really will advance equity across the world and across the field of epidemiology because of the impacts that will have as compared to the commercial software that are currently being used. So the R sort of framework that we've built for public health, it starts with the EPI-R handbook. This is what we launched 1 year ago, but it includes all these other components, and I'll get to them in a moment. So the EPI-R handbook was really a collaboration of 50 friends and colleagues. It was a grassroots thing where we saw this need and we said, let's make a reference manual for public health. And so we got together, and over about 9 months in our free time, we made this R code manual. In about a year, it's been used by 200,000 people, and it's right now being used by 1,400 people every day. So we've been really happy with the amount of people that we've been able to help with this resource, and it's free. It has an offline version as well, and we know it is being used in those settings with low internet connectivity. It's a massive book. It's 50 chapters. It's, I think if you print it out in Microsoft Word, it's 1,200 pages. And it has code examples and sort of like a tutorial feel to it, but it's really just code samples and best practice examples. We have translations going into 11 languages at this point through volunteers. It's been widely adopted among health agencies at that field level use, and it had about 120 contributors from dozens of agencies. Just to give you a feel of the chapters here, there's a section on the introduction to R, getting people transitioned from other software. There's sections on your core data cleaning, grouping, pivoting, etc. Working with dates is really important with epidemiology data. Deduplication is really key. We have a whole chapter on deduplication, and of course, iteration and lists. Data cleaning is really the bulk of the EPI work. GIS, survival analysis, some epidemic modeling, time series and outbreak detection. Flagging these things is really important. We talk about tables. These are really just descriptive tables. How do you make them nice? How do you edit them? Making staple plots like epidemic curves and demographic pyramids, transmission chains. These are things that are really public health specific, and we bring people sample code that they can just produce pretty quickly. Phylogenetics, I mentioned transmission chains. These heat plots are really useful for making specific diagrams in public health. And then, of course, R Markdown, right, and dashboards using Git for version control. We even have chapters on the peculiarities of handling R on government computers, right, which have often firewalls and things like this. A few lessons learned. And challenges that we faced. Well, it turns out in the middle of a pandemic, most epidemiologists do not have a lot of free time. And so that was a challenge to actually write the book. We made it as an independent group. We were not affiliated with any major institution. And I think that gave us a lot of latitude to move quickly and to write what we felt was best for the community without having to go through a lot of bureaucratic hoops. We did have to think about who our audience was, and this handbook is not meant as a tool for a raw beginner to learn R. Instead, it's for someone who already has a basic understanding of R, although we did also write it so that if it was the only resource someone had and they were offline and they just needed to learn R from scratch, they could still get by with this resource. We made several editorial decisions that I'll note. The readability of the text. So, for example, you can see here in this the upper image, we chose specific nomenclature about bolding things or using parentheses, and the way we wrote our code syntax in the examples. the way we chose packages and functions. We have a whole chapter in the handbook about our editorial decisions and why we chose to advocate certain packages over others for simplicity, for stability, for ease of understanding, also with other languages reading how the words translate. And again, you can do many ways to do any given task in R. So we had to really think about, we're going to offer perhaps a wrapper, a very customized function if there is one, but then we're definitely going to offer a more general solution. So an example of that would be epidemic curves, right? There are packages out there such as Incidence2 where they make epi curves very fast, but they're perhaps less versatile. And we think it's important that there's adjacent to that, we describe the ggplot2 methods and tips for making epidemic curves. We also field tested the book with Doctors Without Borders. They have epidemiologists working in emergency settings around the world, and they tested the book prior to its release. I think that was really important. The book itself was over 40,000 lines in Bookdown, and so having it all run seamlessly was actually very difficult. And so that was a challenge. Version control with 11 different languages is quite challenging. Right now, we have a different GitHub repository for each language, but we're moving towards what I think is a more efficient system over this coming months. So I'm sure many projects are working with that challenge of how to do translations with these kinds of book downs. But around the EpiR handbook, we wanted to build this broader ecosystem of support for public health R users. So we have this the foundation, right? That bridge to the EpiR handbook. And this comes in two ways. We have a live course, which is 35 hours, which we've been delivering. And I'll touch on that in a moment. And then we have these self-paced tutorials that are free online using the LearnR package. So the live course, we've been teaching now for about half a year and have received really good feedback about it. Again, it's very tailored to public health. So it does not assume any coding experience, and it goes through really 5 days of what you need to know to get using R as a public health practitioner. We have case studies, there are live coding demonstrations, interactive exercises, all that good stuff. And we do follow-up sessions. So we actually help them apply the R learning to their work projects, which I think is very valuable. And so we are, the approach here is, we're bringing our experience to the course and the content. I think as any person who's taught R knows, you have to be very intentional with the vocabulary you're using, whether it's, are we using the word import or the word read when we're talking about bringing in a data set, things to reduce that mental load on a beginner, and think about them progressing and becoming independent R users. Building that confidence to tinker, as it's called, emphasizing experimentation, trying to progressively having them write more and more original code and becoming self-reliant with error messages. And then importantly, we spend the time to have the students help them set up R on their computer and handle all of those troubleshooting and firewalls that I mentioned that so often accompany use of R on an institutional computer. We've already trained 120 epidemiologists like this, and we have many more coming this year. And you can see here, the demand is really quite overwhelming for this kind of public health specific R training. So the tides are shifting towards R in public health, and it's quite exciting to see. The tutorials we have are sort of the free version, and we have 5 tutorials up on our website, and I'm sure you're familiar with these LearnR tutorials that are fantastic to be able to have people code in a browser and not have to deal with R. They can just focus on the syntax and not deal with installation. And then the other piece I want to talk with you about is the support, because in the long term, I think public health people often work in emergencies. They're often doing things very last minute in those emergency settings, and they're going to need some kind of support longer term as they learn R and ultimately teach R to their own colleagues. The first step we've taken on this is building Applied Epi Community, which is a discourse website. If you haven't learned about discourse, it's a great way to make a forum. And it's similar to like a Stack Exchange, except the intention with this site is that it is very welcoming of beginners, very forgiving of, for example, making reproducible examples, making mistakes with that. And it's embracing the public health context behind the questions that users ask in this site. I think we want to not so much strip a question down to the bare code, but also embrace that public health context. We also have, it's also space for non-R questions questions about methods for outbreak response and surveillance, or genomic epidemiology, or mathematical modeling. And we're also having a beta tester group in this community site that we've linked with some big agencies who are trying to professionalize the R package for public health ecosystem. And so we're going to provide support as a beta tester group to make sure that those engineers are able to really solve the problems that are facing the users, and that feedback gets back and forth. And just an example of this, you can see that people can post questions, and then typically like a Stack Exchange, you can select the best answer, and it's really welcoming of a discussion format. The second piece to the support that we're building out is the R help desk, and this is something we're piloting at this stage. But the idea is that, like we have a global cadre of instructors around the world right now who will be teaching and are teaching our R courses, we will build out a cadre of R technicians who also know public health, who can provide a kind of help desk support, whether it's troubleshooting an error that otherwise would have taken them 2 hours to figure out the answer to. They can simply call us or post on the community, or if they really need a fast response, they can do this help desk. Code review, people who are deployed to emergencies and you need to quickly set up a data pipeline from data collection in clinics through a sort of central emergency operations center, and then producing that into actionable intelligence for the emergency response. Those kinds of things can really be improved with R. And so we'll be on call to support those, working with WHO and other partners on the ground. And so I think I want to draw to a close building the R community. What are some of the things that we can draw from the work Applied Epi has been doing, thinking about building our community? The first one is, what are the disciplines out there, like public health, for which R adoption would result in tremendous real-world impact, but has not yet been made easy for people? So in that discipline, how do we accelerate that transition to open source software like R, to really have that impact of reproducible analytics, the collaboration benefit that comes with being free, the ground level problem solving that comes with being able to contribute as an open source software? I think we need to be aware of these communities and make sure that the language we teach R in is not alienating and not scary, quite frankly. I think a lot of the experts in R come from a very technical background, and it's important that we bring the language of the everyday user into the training materials that we create to try and invite them in a welcoming way. How do we bring those practitioners into these communities of practice? I think a lot of early adoption of R happens in, like I said, more technical, perhaps even academic spaces. And so, at least in public health, we need to think about how we bring in those practitioners who might not be clued into these communities of practice. That's what we're trying to do. But I think there are lessons maybe perhaps for other disciplines as well. What are those barriers to adoption? Whether it's the fact that people have never even conceived of themselves as coders before, making the language very accessible, things like even the word string, right? This is something that for someone who isn't in the world of sort of computer and data science, they are not thinking about text when you say the word string. So making your words very intentional and your progression intentional. How to create linkages between developers and programmers and those front-end users. I think we need to have constant feedback, both in the direction of what are the actual needs and make sure that the development happening is actually addressing the needs on the front end. And when there are tools being developed, that feedback is able to come back rapidly and in a timely manner. These Q&A spaces, I think I talk with many people who say, I love perusing Stack Exchange, but I would be terrified to post something on there. So I think that there is an interest in consolidating these spaces, but also there is room for discipline-specific discussion spaces as well. And so I think there's a balance there that we can find a happy medium with. And then I think, at least specific to our world, how do we secure funding to, once there is the need for R is recognized institutionally, how do we pitch ourselves and say, this is something that big donors and funding entities should actually contribute to create those institutional R champions who will then train their colleagues and provide a network of support in their regions, and fund a big train-the-trainer campaigns, quite frankly. And I also wanted to mention how impactful the translation was for our team. The fact that hundreds of people came to us without being prompted, saying, I would love to help with the translation of the EpiR handbook into all these languages. Instantly, it gave our team a global reach and a network of practitioners who were keen to push R. And so I would encourage any other project that's pursuing something like this to think about translation as a mechanism for having a global relevance. And so I'll close with that and our contact information. And I would love to take questions and have a discussion with you about how this is relevant to the rest of the R user community. Thank you very much.
Thank you. Yeah, I actually don't think we have time for questions right now, although you, Neil, can go into the Q&A and answer questions by typing as we are moving on to the next talks. I do want to echo what Nick was saying. This is an incredible piece of work. Like, it's so much stuff that I did not know about, and I'm really excited to learn more about it. So thanks for sharing.
Thank you.
So now I think we're gonna swap back to the what was scheduled as the first talk, and we've moved things around a little bit. And I'm gonna introduce Nadia Bodner, who is a postdoc at KU Leuven. Do you want to try sharing your screen?
I'm going to share that. No, that's not the right one. Do you see it? Or
Not
am I
yet.
sharing the? Okay, I'm sharing the wrong one then. I want to share that one. Is that okay? No. Are you seeing my slides now? Wait.
Not seeing anything yet.
I'm trying to share the same slides as where I see you on. But so probably I got allow it and then I try it. Is that okay?
There we go.
Yep,
Now I can see your screen. Yes. Yeah.
Okay, sorry. Yeah, sorry. It seems a little bit like chaotic because I'm also on a conference and it's 6 o'clock in Belgium here. Well, eventually I'm talking about contingency measure-based networks, and I'm here just in one of the back rooms of a big institution where I found some place to give my talk. Well, eventually we developed a R package that's called Connect, and it's about contingency measure-based networks. Well, about the background, I'm a psychologist and I'm working at KU Leuven in Belgium. And what I'm eventually working about is microcoded parent-child interactions. And we linked what is happening in these interactions to attachment, to depression, to cultural differences. What we're eventually doing is videotaping interactions that are coded afterwards in second-to-second intervals for the presence or absence of behaviors. That means we've got binary time series from these interactions, and we want to have some impression what is happening in these interactions. And therefore, we want to depict it as a dynamic network picture. I developed a R package for that, and we divided it in 4 modules, which I will talk you through very quickly. Well, eventually, module 4, I will include that in the talk and show you what does that, for example, data exploration mean at this moment for the network. Okay, we have different data included. There were mainly other researchers that came to me and were asking for help. There's attachment data from mother and child that were coded during a stressful interaction. There's family data of a mother, a father, a child that or an adolescent that is coded during a problem-solving interaction, and there is symptom data, which I will mainly use as an example. Well, let's take a look. First, there's visualizations in there. So you see here, for example, the 8 core, the 8 depression symptoms that were reported by the participants over, in this case, with this participant, it was a course about of almost 3 years on a weekly basis. You can, for example, visualize that with these intervals, or you can do it by a line that is at one level when the symptom was shown or not. That gives you already some impression about what is happening here and which symptoms. The research question here was mainly from which symptoms do occur at the same moment. When we look at time series, you need to take a look at the relative frequency with which the symptoms are shown. But what is even more interesting, you may have noticed that it's very likely in this kind of time series that a certain symptom is more likely to occur at a moment when it has been shown the week before, which is quite likely. And the same is true for interactions, of course. Somebody is normally not angry for 1 second, but for longer times. You can calculate that from your data, and you also can visualize that. What do we do with that? Well, the relative frequencies we use to create our nodes of our network. So each symptom is a node, and the size of the node depicts how big the relative frequency is. In a second step, now we want to take a look from how many times do these symptoms occur. In this time, we wanted to show at the same time. If you look at the right side, you see these arrows that are without lag at the same moment. But you could also ask, for example, in an interaction, how likely is it that somebody reacts angry if somebody's been angry before? We do this, we quantify that with contingency measures. You may know probably Cohen's kappa, but proportion of agreement is another one. Classical and corrected Shakar is one that I developed and use a lot. But you could also use a phi correlation coefficient, odds ratio, or log odds ratio. Well, what's the difference between those? There are 71 of those out there, as I read in a paper recently. The first thing is whether the co-absence, for example, is accounted for. Which might not be useful in interaction, but maybe might be useful in depression data. Whether there's a correction applied for the relative frequency, and how the range is defined. For example, I often use the Shakar index, which you see depends on the number of time points that the first and the second behavior are shown at the same moment as a ratio over that at least one of those has been shown. You can then, here I refer to the family data with mother angry, father angry, adolescent angry, mother dysphoric, and so on. You can show that in a kind of a contingency matrix. And if you're not content with the contingency measures that are included, you can do one yourself. As you see here below, it's quite easy. I used QuETS-AC, which is mainly an inter-rater reliability measure. One of the questions that you might ask yourself is which leg to take. Therefore, we included a feature where you can take a look at what makes difference. And you see here, for example, that mother happy and father happy, what you see in the first row and in the second column, has some kind of a lag of, is biggest at a lag of about 1 or 2. This might give an indication. However, in many cases, it's better to decide this on theory because there might, for example, happiness might be very co-occurrent, while anger is better if it's taking, it is probably more turn-taking, that somebody is angry after somebody else has been angry. So we calculate the contingency measures for different legs, and then you could make a decision on that. What does this mean? Well, these measures then quantify the links between the nodes. So we, of course, we left away the outer loops because, yeah, of course, core occurs at the same time as core every time, so it's a 1. But for example, what is nice here, you see that, for example, also core and cognition occur always together. So there's a big link in there, while, for example, guilt and energy is much lower link, a much lower strength. Well, eventually there's a problem with that. especially the Shakar index, but many others as well, depends on relative frequency. As you see in these plots, you see the U-shaped form of proportion of agreement, where the proportion of agreement is if you've got two statistical independent, which are just random to each other, is the lowest with 0.5, and it's automatically very high if we've got a relative frequency of 0.1 or 0.9, while the Shakar index, for example, gets higher and higher the more the proportion of agreement is. The other thing is, which I will not go in too much detail now, is that the serial dependence also gets your distribution broader. As we already saw, it is very likely to have a certain symptom if you had it the week before. And of course, if then a symptom co-occurs with another symptom, you also have, it's very likely that they co-occur not only for 1 second, but for more seconds. And if they don't co-occur, the probability is very likely that they don't co-occur. Well, eventually what you get is more likelihood for higher or lower values, which makes your whole distribution broader. A value that would be considered very exceptional, for example, take Shakar index as the middle column on the right side. You have 0.1. That would be rather exceptional if we've got this kind of relative free, this kind of Shakar index. If we don't assume zero dependence, but if we do assume a high zero dependence and the lowest in this very black distribution, it's still high, but it's not that exceptional. So we need to correct for that. Well, what did we? We developed a significance test that has, for example, you see here the 2 time series of guilt and death, which is of course not death, but preoccupation with death. And what we do is we make some kind of independent surrogate data, and we get a distribution, and we calculate on all possible couples the contingency measures. So what you get is your step 2. You get the real contingency value, and you get your distribution. And then you could, for example, do a significance test by taking a look whether your observed value of the value of your observed data is higher than, for example, 95% level. How do we do it? Well, we take our time series and we chuck it in chunks, and then we rearrange them. So we get some randomness in there, and then we shuffle it around. So we get independent. Well, what is the consequence for our networks? Well, part of the links we quantified before is eventually driven by the size of the nodes, or other speaking, by how often and how frequently the certain behaviors are shown, or certain symptoms are shown. You can also take a look at the distribution yourself, because you always calculate it. And well, what about networks? I just want to give you that example that we had before of the family networks, where you see, for example, you've got the happy emotions in yellow, the angry ones in red, and the blue ones are dysphorics, of course. And you see there's a lot of going on during this conversation. It's a problem-solving task between the adolescent, his mother, and his dad. But you see that, for example, as a practitioner, you should, for example, focus on that link between adolescent and mother, or on the happiness, or on the dysphoric. You see that there is this might relieve a pattern which you can use and talk about afterwards and practice. And what is maybe special about my work is that I always went, like what Neil said also, from the real problem that people had to solve it, And well, eventually at the end of my PhD, I decided that I want to make that available for other people who are dealing with binary time series. There's a lot more about to tell it, but yeah, I just may give you the idea to take a look at my package, and you find the link of the tutorial paper in there. So feel free. And if you've got problems, please reach out, or you've got additional ideas what I could do. And then I've got to stop it. And
Great.
I'm happy to
Thank
hear
you.
questions.
Yes. So, folks who are here as attendees, you could put a question in the Q&A tab if you wanted to. Folks who are here in the session are welcome to ask questions out loud. One of my questions was sort of about the way that this data is structured. It felt to me like it was going to be dyadic data, which I know has a particular type of structure, but then it's time series data. So can you talk about how it needs to be formatted?
Well, yes, the format is mainly that you've got time series data where you've got seconds or the time intervals in rows, and your variables as each variable is a column. That's the most easiest way in our data to read it in at this very moment. But of course, yeah, you can transfer it into this direction. And it's also, if you want, especially if you want to do the significance test, you probably should take a look on data of more than 100 time points.
Okay, great. And then it sounded like you were doing kind of a simulation method for your non-parametric inference. And so you're sampling, are you resampling from the existing data so that it has some of that time series structure?
Yes, I want to keep the relative frequency and zero dependence as much the same as it was. And therefore, we decided, well, there's two methods in there. The one is just is a method that just reads out. There's a modeling approach that reads out the relative frequency and the zero dependence, and then simulates with a Bayesian, with a Bernoulli model, a time series that's more or less equal. Of course, there's more randomness on this because you simulate it. And the other one is that I want to propose, because that one is working really nice if you have some time, but if you only have very rare data, it gives sometimes weird results. But you've got your time series and you chuck it in chunks. And then you destroy your serial dependent, your relative frequency is exactly the same because you just reshuffle it in, for example, 10 chunks, and you reshuffle it. And your serial dependence is only interrupted at 9 points, so that's not that much. But by reshuffling it and putting it together with the other time series that's also shuffled, you destroy the connectiveness between those two, so you get rather independent data. And in this way, you can make a distribution that is of independent data. We put some randomness on there because normally it's not dividable by 10. And then sometimes the first is the longest and the last, and some, yeah.
Great, thank you. Are there other questions from folks? Okay, well then I think we're going to move on to our next speaker, who's Kieran Martin, the R engagement lead at Roche PD Data Sciences, and I'll let Kieran share screen.
Great, thank you. Let me just one. Okay, that's showing. Cool. Okay, yeah, so I'm going to talk a bit today about our journey at Roche in transitioning to R. So yeah, just briefly on me. Yeah, my name's Kieran. I'm the R enablement lead at Roche, and I've been at Roche for about 7 years now. So Roche, if you hopefully most of you have heard of, is a pretty big pharmaceutical company. I think we've got something like 70,000 employees, and I'm going to be talking pretty much today about one department, the department I'm in, which is product development data sciences. If you don't know what that is, which I wouldn't blame you, our role is basically to report the results of clinical trials. So we get lots of raw data on the performance of our drugs in terms of both its safety and efficacy. And our job in data sciences is basically to take that raw data and turn it into tables and graphs demonstrating what those profiles look like. And one key aspect of that that sort of impacts our transition to R, and I'll get into later, is that we're quite a heavily regulated industry for good reason. You know, we're dealing with patient data here, and it's really important that the results we provide to health authorities we can demonstrate reflect what the raw data actually says. So in terms of the department, it's pretty big. It's not as big as the whole of Rush, but we've still got around 1,000 full-time employees. And then on top of that, we've got lots of contractors and also external resource. So other companies that we partner with to report on clinical trials. So what I'm going to discuss today is basically our transition to R, that's RR, core data science tool for clinical trials reporting. So it's probably not going to be, well, it's definitely not going to be the only tool we use for programming, but it is going to be the one we're focusing our development on, and it's the one we're going to be encouraging people to use in their work. And this is a pretty big change for us. We've been using the same programming language for basically everything for a really long time. So it's a pretty big transition, and there have been a lot of things to consider. And I will say that this is all part of a journey that we are going through right now. So when I'm talking about the sort of solutions we've picked for solving the problems, they're solutions that we don't necessarily know will work. We're pretty happy with how they're going so far, but I'm sure that in like 1 or 2 years, I may have to give a presentation where I have lessons learned and I talk about the things that maybe we could have done differently. So just to go through what I'm going to discuss, I just want to give you a brief history of R at Roche to sort of motivate why we're doing this transition right now. And then I'm going to spend most of my time talking about the transition to R and what's involved in that. So looking back something like a decade ago, as I kind of mentioned, SAS was and remains the programming language of choice in data sciences. So effectively all of our code was in SAS, and R was available, but it wasn't commonly used. It would be a minority of people in the department who could program in R. And typically when it was used in kind of edge cases, often by statisticians who were doing some kind of simulation study that was a little easier to program in R. Or one example would be like novel statistical methods which weren't implemented in anything other than R, where they wanted to explore something. But that was very much an edge case rather than something that was happened very commonly. So something like 7 to 5 years ago, this started to change a bit, and there were a few reasons for that. One was just a change in the terms of the talent that was coming into the industry. New joiners were much more likely to know R and Python than they were SAS, and we were often in position of training people from scratch in SAS because they just hadn't seen it before at university in particular. And the other kind of really big wedge for making R more popular in the department was R Shiny. It provided a capability we didn't have already, because one use case we often have, I mentioned earlier that we're sort of delivering these collection of outputs to health authorities. And while that's something we absolutely do, during the lifetime of a study where you're collecting data on patients, obviously there's lots of people who want to learn about that information. So we have scientists who want to find out, that they want to look at a particular subpopulation, maybe a particular age group, and see how they're coping with that drug. And they'll what they'll do is they'll go back to our department and say, oh, hey, can you provide us a view of this data? And we'll go ahead and make that view, and they'll look at it and they'll go, oh, that's interesting. I've noticed a bit of signal here. Can you provide a different view of that data? And when we go back and do that, and that cycle could be quite slow because while it doesn't take very long to program a particular view of the data, it's kind of that feedback cycle of I make the view, you look at it, and then I make a new view. So the obvious solution to this is making it interactive. Building apps in R-Shiny allowed us to produce tools that our scientists could use to get instant understanding of what the data looks like without this needless feedback loop in there. So what this led to was a kind of critical mass of R users. So we had more and more people who were experienced in using R, but we also had this gap where we were creating these views of data in these R-Shiny apps. But when it came to reporting to health authorities, we had to kind of recreate those outputs from scratch because we didn't have the capability to deliver them directly from the Shiny app. So the idea was we wanted to be able to use R in our regular clinical study work, so use it for reporting to health authorities. So about 4 years ago, we did build an environment for doing so, and this was validated for limited use in clinical reporting. So you couldn't do everything, you could do some bits of it there, and this was great. It filled a need, but it definitely was limited. It meant that you kind of had to split your code base between SAS and R because you couldn't do everything in one language. And it also, because it was built in this sort of quite quick way, there were functionality missing there. And we really wanted to go further than that. So that's kind of where we are now in our transition to R, is our goal is to enable and start doing full reporting in R. And that means we need a validated environment for using R end to end. If the word validated doesn't mean much to you in this context, it's a big word in the industry, but basically it essentially means that we have to prove that our software and our systems do what we say they do. So we document what they're meant to do, and we have some tests to demonstrate that they do that. And doing that validation can be a big effort, and it is a collaboration. It's not just our department. We have to collaborate with our partners in IT and also our quality departments to agree on what validation in R looks like, because this was all new for us, particularly 6 or 7 years ago. So getting into transitioning to R then, I think there are kind of 3 components when you're thinking about moving your code base from one language to another. And those are the system that you're working in, so where you're running R and the features of that. There's the tools, so the R packages you build to support your work. And last and probably the most important is the people. Getting people ready to work in R. So I'll go through those in a bit more detail. So one really important use case when it comes to doing analyses in a validated setting is you want to be able to reproduce it. So there's lots of use cases where you might need to recreate the results you delivered 1 or 2 or even 5 years ago, and we need to be able to do that. So fortunately, technology has come along which mostly solved this issue for us. It's not just technology, it's technology kind of plus procedures. So one part is Dockerization, so building images or snapshots of your operating system and the version of R helps fix that in place. But the second part for anyone who's familiar with R is the packages, because if pass my analysis onto someone else and they have different versions of the packages, they're going to get completely different results. So we've standardized that using 2 different solutions. One is using RENV, which allows us to take snapshots of which packages we're using in a project. And we're also using internal package repositories to allow us to take snapshots of suites of packages at once. And that kind of leads into the second part of validating is how do we validate our packages, which was a big question for a while. Just, if I've picked up an R package from CRAN, how do I know that it's going to give the results that it says it's going to? So there's been a lot of cross-industry work on doing that. So I've got a link there to pharmar.org, which is the risk validation hub. And there's been loads of collaboration from different companies on how we define a package to be high quality. And we collaborated on that, and we turned some of that into our in-house solution to allow us to validate our packages quite quickly. And what's nice about the solution as well is that in the past, I've been in companies where, sure, they've allowed us to use R, but it's really like 10 packages that have been validated. But this solution's really flexible, so we can add in more packages as and when we need to. So we don't lose the advantages of R while still, having that validation layer. So the next part I wanted to talk about was the tools we're using here. So when we're doing clinical reporting, a lot of what we're doing is pretty standard in terms of what we do with the data and how we report it. So it would be quite wasteful for us to try and get everyone to build things from scratch in R, and certainly that's not what we were doing previously. So we've already done a lot of work in building our packages for solving these problems. We've still got some work to do. But one thing that we're really excited, I'm really excited about, and with the company really excited about, is the ability to open source these packages. So for if you go to those links, so the Pharmaverse is actually a cross-industry collaboration to build this sort of suite of packages that we can all use in clinical reporting. And we've actually just, I think last week, open sourced I think all of the Nest packages, which were our in-house reporting packages, which for a long time we were sort of going back and forth on. So I'm really pleased to say that they're now open source. So you can go to that final URL, Insights Engineering, and you can see all the different packages we use for creating tables and graphs. I think it took us a while as an organization to get on board with open sourcing our code base, but I think it's really for the better for all of us. I think ultimately, if we have open source code, it's going to be higher quality. It's going to reflect better modern data science practices. And it's also easier for the regulators because it means they don't have to see 5 different versions of solving the same problem. And it just makes things easier across the industry. And one, for me, thing that really sold, I was already sold on open source, but one thing I like to show to people who are sort of reluctant about it internally is an example from one of our packages we've had open source for a while, which is R tables created by Adrian Waddell and Gabe Becker. Where this is open source, and you can see Joe Chang has actually given us a pull request there, noticing that we were using an HTML tools feature for producing HTML tables, and he probably picked out this feature that our developers would never notice. So it's really great to get those contributions from the wider R community, and I think it's just a really a big advertisement for open source for me. Is just that this is an example of it, really. So for the last part, which I said was most important, but I know I'm running out of time, but I want to talk about a little bit, is getting people ready to grow into R. So one thing about having a big department, I mentioned we had this critical mass of R users, which we do, but we also have plenty of people who haven't used R at all or used it a little bit, and have different ideas about whether they want to use R or not. So approaching that has been really important to build a sort of multi-factored approach when it comes to learning. So that means not just doing one thing, building loads of different resources for that. So one thing we've done is curated a really rich library of offline resources, so resources people can do in their own time, which includes kind of the best quality content that's available online, either stuff that's free or we've paid content for, and also internal training that we've customized for that use. And then on top of that, we of course do in-person training. And one important part of that is base it on real life examples. So as much as possible, make it connected to the work people are doing. And sort of following on from that, one really important feature of training for me is making it just in time. So basically doing training just before you're about to use it. That's really, really important. And it's something I've certainly made the mistake of in the past, and I'm sure others have, is it's very easy to take a training and then not apply it for several months, and then you essentially forget everything. So that's a really important feature, is just making that training at the right time for everyone. So the last couple of things in bringing people across is remembering that we're a community and mentoring people together. So we don't need to do this transition all at once, and we're very deliberately targeting different teams and making sure they have that support they need to learn together as a team. So yeah, I think I just want to finish by saying this is, as I said at the start, all part of a journey, and it's not going to end when we've kind of transitioned to R. We're going to keep going after it, as we want to be more flexible in the future to be in a position where we can kind of pick the right tool for the right problem. We can use Python or Julia when we need to, and we as an organization kind of don't get stuck in one place, and we're able to move flexibly in future. Yeah, so thanks very much, everyone, for listening, and I'm very happy to take some questions.
Great, thank you. Yeah, I think we have time for one quick question. I see one in the Q&A tab. It sounds like you also considered Python as an alternative to SAS. What made you choose R over Python?
Yeah, I had a slide on this. I think in terms of it's a balance of like the talent that's coming in. I think a lot of them know more R, and I think as a tool for statistical analysis in particular, I think R is still a bit superior. I think also, just things like ggplot, Shiny, those things that they are being created in Python, but they're not quite there, I think. So, if we were more focusing on machine learning challenges, I think we definitely move to Python. But at the moment, we're doing more traditional statistics, and I think R is still best there.
Great, thank you. And with that, we'll move on to our last but not least speaker, Nicholas Tierney, who is a research software engineer at Telethon Kids Institute. So take it away, Nick.
Wonderful, great. So thanks everyone, and thanks for the great talk so far. It's been really awesome to, I don't know, been a bit out of touch with the R community. It's really exciting to see so many awesome people do great stuff. So I work as a research software engineer, and I work at the Telethon Kids Institute, which is like a research institute attached to the Perth Children's Hospital in Western Australia. And if you'd like to follow along with the slides, you can go to this link here, njt-user-2020.netlify.app. It'll also be on the bottom of my slides. Hang on. There we go. Okay. I work as a research software engineer. That is my job title. And I work within this research institute inside the Malaria Atlas project. So it's a group of about 20 to 30 epidemiologists and disease modelers who work on providing malaria projections and current estimates for the WHO and various other government bodies. I primarily work with Nick Golding, and the main thing I do is I work on the Greta software, which I'll explain what that is in a moment. Just want to give a bit of context about what my role is and like where I sit, and I'll explain a bit about what I do. But I'm embedded within the team, and I'm not usually consulted out to teams to do specific software jobs. That did change briefly last year, but that was a special case where we needed to provide some estimates to the Prime Minister's Cabinet of Australia for COVID modelling, which was really exciting. And mostly what I try and do is I develop software to help teams for specific research problems. And I have a mixture of remote and at workplace working. So I create software to solve research problems. And part of this is to develop the tools that abstract the right components to facilitate research. I also try and help researchers find and learn good tools, as well as support them with computational reproducibility. In the past year, I've been in this role since March last year, and I've been working on understanding, improving, and maintaining the Greta R package for statistical modeling, as well as developing new interfaces for statistical methods, and and doing COVID modeling for the Australian government as part of a large team at a small role. So briefly, Greta is it's a really powerful R package for doing statistical modeling in R. It has a simple interface, and the back end of Greta is powered by TensorFlow, so it scales really well for certain types of data analysis. The package is named Greta after Greta Hermann, who wrote the first algorithms for computer algebra without a computer. Nick Golding has decided to call it Greta, spelled as is, to avoid people saying Greet, just because the spelling of her name for native English speakers might not be said in the same way. Greta was designed to look roughly similar to how you might write an equation. So on the left-hand side here, this isn't typically how you would actually write an equation in terms of the order, but say like you have some priors on alpha beta and say for standard deviation, and then you say that y, the likelihood for y is a normal distribution and parameters mu and sigma. You would then specify this, say you could assign x and y here in R code. You have your priors alpha beta and your standard deviation, and you have your likelihood. You're saying that y is distributed as a normal with parameters mu and standard deviation. You put these into a model object, and then you run MC on these. So there's a lot happening here, and we're abstracting over a lot of components. It means the software underneath is a bit more complex, but just to give you a general sense of what this does. And so some of the other work I'm doing, I'm just going to quickly, there we are. So I also work on trying to design new interfaces. And as part of that, say we take an example with malaria modeling, which is what the group does a lot of. After sitting with some researchers and seeing the code that they wrote, I was able to distill it down into a couple of key components. So they had a data cleaning step that had a lot of repeated steps where they were creating effectively these indexes for specific regions and countries, and they were repeating a lot of steps here. So they had a data cleaning step, and then they had another step involving some software called InlaBrew, which sits over top of Inla for Bayesian modeling. And it involved a lot of repetitive steps where they had similar kinds of patterns over time, like using an AR1 process. And we looked at this code and we tried to design an interface that we thought might be more intuitive for the researchers. And we came up with something like this, where the researchers specify a formula, and then they wrap up the hierarchical time component, the WHO region and the country. And then this function writes all of the data cleaning code as well as all of the modeling code. Admittedly, this is to fit a very specific type of model that they had to fit a lot of. But the concept of this, we couldn't get this to fully work with all the researchers. We had to do other work with COVID. But the idea with this is to try and focus and design the tools so researchers can just focus on the bits they need to, rather than all of the data cleaning and all these extra steps of all these models. This is not to say that our software is better than Inla. I think Inla is an amazing piece of software. It's incredibly flexible. It's just that there's a specific way to abstract and cut along one axis to design software. And that's sort of part of what I think is important and cool about working as a research software engineer. Now, this part of the talk is reflections and advice. So what I'm going to do here is I'm going to talk about just a bunch of stuff that I think is interesting and that I wish I'd learned, and some stuff that's happened over the past year. So the Greta software is really complex, and I was like, how do you start to look at this? So I had used it a little bit before I started this job, but there's 11,000 lines of code, there's over 1,500 tests, and there's about 700 functions. And it's a lot to think about. And so you can think about you just read each source file in alphabetical order from start to finish, which is actually something that I did. But if I were to think about this again, I think I wish I had been slightly more structured. I still did keep notes, and I don't think it was totally insane. I did know about the code, but I would say to people taking on new code bases, I would say keep a notebook, like a Google Doc or something. Get familiar with the code and use it. Go through the vignettes, read the help files, use the code again, read the vignettes again. And I say this as recently I reread a vignette, and a lot more things start to make sense. This is after working on this for a year. So just make sure you keep reading the things that people have written ahead of you. and keep notes with the questions and unexpected behaviors, why things behaved a certain way. And I was able to work quite closely with Nick Golding to sit and have a lot of meetings with him to discuss specific design decisions and also what certain bits of the code base did. And ultimately what happened when I started reviewing this code base is I kept a Google Doc with a lot of thoughts and ideas reading the software, and I had about 16 pages of notes at the end that I then collated and moved into sort of similar types of topics. And that was how I started to get a grip with the new code base and then decide the best, easiest things for me to implement. The other thing that I'll say is you can read the source code, but reading the tests is actually really elucidating. It's a really good experience to get a good sense of what the what you expect all the code to do. So I'd say that that is a really good thing to do, but you should definitely do both. Read the source code and the tests. So I've got a slide here. You can smell without doing the cooking. So there's this idea of code smells and feels, which Jenny Bryan gave a really good keynote and user in 2018. And she describes a code smell as an evocative term for that vague feeling of unease we get when reading certain bits of code. It's not necessarily wrong, but it's not obviously correct. And so what I mean by this is that you don't have to design the code and can have this really strong, deep understanding. You can still read through code and identify things that might not be quite right without like having a truly deep understanding of exactly how every single piece fits together. So you can identify repeated error messages that might just be the same thing. That's a copy paste thing that you could fix. Rewording error messages is another thing. Something I picked up on recently was that there are a few times where this code was written here where you're applying over some object, the function length, and then returning a number. But the thing is that there's actually a vectorized lengths written in base R. It was relatively recent, in the past 5 or 6 years, I believe. So I was able to change all of these expressions of code to this as a small example, without specifically understanding like how this thing is used or like why it's used in that specific case. I know that this is a code pattern that I can identify, just as an example. The other thing I would say is using snapshot tests. So when you test your code, you want to make sure the output is consistent. So you want to make sure your code looks like this when you print out a Greta array. If you want to use the tests, like to test that it looks the same, you create this object as a matrix, and then you have this output here where you paste then like what this looks like, and it looks all garbled and it doesn't look anything like this because you have to write it sort of a bit more how the computer sees it, and you have to write some code to make sure you evaluate it correctly and stuff, and there's all this extra headway. But you can use a thing called a snapshot test, which just allows you to say, make this thing and then do a snapshot. And then you validate the snapshot once, and the snapshot is stored in a markdown file, and it looks like this. And this is really nice because it means that the intent is much clearer, and you can also visually inspect these snapshot tests as you do your testing. What's really, really nice about this is that you can do this with error messages. So previously, we had to write something like this, where you say, you expect an error if we give it this code here, and the error is going to look like this. And it's going to have this message that's written like this, and then we do this again. So we have another thing. What happens if we give as data a list? And I have to say, okay, it's going to look like this error here, because we wanted to match exactly that the error message wasn't changing. But with a snapshot test, you can just say, expect snapshot error, and then the thing that produced the error. You can do that again and again. And what's really nice about this is that you then get all the error messages in one markdown file. And so this was a change that I made with Greta, but it was really nice because it meant that we could then review a lot of the error messages in one document rather than trying to go through each of the bits of code and review the error messages and understand what they look like and how it would be interpreted. We can sit here and we can look at what they actually look like to the user, and it allowed us to actually rewrite a lot of the error messages to make sure that they were clearer for people and much more helpful. Some other pieces of advice I'd say as a research software engineer: use version control. If it's Git, Mercurial, Subversion, something. Use GitHub or Bitbucket or GitLab. Use some place to put your code for other people to see it. And I'd say if you develop new changes, make a new branch, the minor inconvenience of making a branch is worth the relief when you realize that you've like horribly changed things, and you can just ditch that branch and forget it ever existed and move on. I would say write useful commit messages. So do finish the sentence, this commit will ... to say this commit will use message instead of stop as a commit message. Don't write some of the commit messages that have just plucked from my own history of no hyphen or try putting dev mockery back. These aren't necessarily the most helpful things. Just want to credit Adam Gruer for that. This commit will ... which I think he heard from someone, but I heard it from him first. It's really helpful. You can save time with PR fetch and PR finish. Let me quickly check the time. Okay. These functions are awesome. They save me time every day. PR fetch grabs, say, the pull request number 101 from GitHub into your local session. And then after you merge that, say on GitHub, you can write PR finish, and this will delete it locally and delete it remotely, and also make sure that where you're currently work to is then where the main branch is. These are just small things that really help. And there's plenty more in the use this docs. How am I going for time, Amelia?
You've got a couple more minutes.
Cool. Brief round about continuous integration. So continuous integration means that you can run your code on someone else's machine, in this case, GitHub, and you can run your tests and check that things work. And this is in theory a great thing. And it is. It's just that sometimes you spend a long time waiting where you have all these green ticks, and then these have all run in less than 10 minutes or 16, and then you wait for the Ubuntu build to finish, and it takes 24 minutes. And then you get an error from something, and then you like Google some obscure error message, and then you realize that you've specified something here, shell R script instead of shell R script. I spent like a day debugging this, and it was just an uppercase S instead of a lowercase s, and realize that there's like another day where you like debug something else and there's a missing curly brace. So sometimes just with the syntax of GitHub Actions and continuous integration, you just end up in a bit of a frustration. And sometimes it feels like 90% of all of my time last year was just getting GitHub Actions to pass. And it felt like there was this always failing paradox. Like if your tests fail, does your software actually work? And like it probably does, because if a single test fails, it doesn't mean your whole software is broken. But it meant that while I was making a lot of these changes and changing over things to GitHub Actions from Travis and a few other things, it was in this place of it's not any more broken than before. So I had to like manually work out in my head how broken it was, and then make sure it wasn't any more broken. And that was a bit brain melting. I think I'm just gonna skip to this point here. I'm gonna say that R packages aren't always the answer. As much as I think R packages are great, not everything needs to be developed as an R package. Sometimes analysis code that you're writing for a specific project can just stay as it is, and it doesn't have to be packaged up for reuse. Miles McBain has a really good blog post on this. In terms of the future, as a research software engineer, this is a relatively new position, and in terms of getting recognition for writing software in academia, it's not great, but it's getting much better. In the past 12 months, we've had an article that's on Roche, Chris Woolston, called Why Science Needs More Research Software Engineers, which was published in Nature. The Monash University Business School has now recognized software as first-class academic output. The Stats Society of Australia hosted a panel on research software engineering. There's an ASIMS podcast on acknowledging research software in academia. I've delivered a seminar called Acknowledging Research Software in Academia, and the Statistics Society of Australia has now developed 2 awards for statistical software, the Di Cook Award and the Venables Award for students, and for like a national prize. So I think we're making progress towards getting credit for software, and I think that that's really encouraging, really exciting. We're making good forward progress, but more work still needs to be done, but it's getting there. I want to thank these people. These are just people who in my career have been really helpful and provide guidance and have been in inspiring people to look towards. So thank you to these folks. And I think I'll wrap up there.
Awesome. Thank you so much. And for folks who are here, I did drop the link to the slides in the chat. So if you wanted to look at those slides that Nick had to kind of speed through, I know you could do that. I think that we are about out of time for our session. And so I think I'm just going to say thanks to all of our speakers for presenting and kind of rolling with the punches today. And thanks to the folks who attended, and enjoy the end of USAR.
Sounds good.